In previous lecture, we have studied one of the most important applications of Saha's theory of thermal ionization, and that was the determination of degrees of ionization of an atom or an element. Today, now we will discuss its another important application, and this application is actually the analysis of stellar spectra. You know, the cause of invent of this theory was actually the explanation of stellar spectra. So we will study this application, which is the root cause of this theory. We know from Saha's theory of thermal ionization that x square over 1 minus x square p equal to 2 pi me over h square whole to the power 3 by 2 kt to the power 5 by 2 Ga plus over Ga times e to the power minus u over RT. You have already derived and studied this very equation, which is known as Saha's equation or Saha's formula for thermal ionization. In this equation, the terms used are usual, which you are acquainted of. Now you can see this x is actually the degree of ionization, or you call it fraction of the neutral atoms that get ionized. So this is fraction of ionized atoms, or you may call it degree of ionization. And we see from this equation, which is actually called Saha's equation, that this x is actually a function of three parameters. The first one is the pressure P, second one is temperature T, and the third is U, which is actually the ionization energy. So this x depends on pressure, temperature and ionization energy. You can see from this result that when this quantity temperature will increase, the rate of ionization will increase. So as T increases, ionization increases, and at the same time P is another factor affecting the value of x, but the effect of P is just reverse of T. You can see from this equation that greater P suppresses ionization. It means whenever P increases, ionization decreases. And the third factor U, if U is larger, this factor will be smaller, and this results for a smaller in that condition the ionization will be larger. So larger ionization results for the a smaller value of U. For your convenience, I am just writing these facts in very short step. So you can note from this result that number one, as T increases, ionization increases. So larger temperature is the most favorable condition for ionization. But on the other hand, greater P suppresses ionization. Suppresses ionization. It means with increase in pressure ionization decreases. And number 3, larger ionization results for the smaller value of P. A smaller value of P. Now we will actually explain the stellar spectra, that is spectra obtained from the radiation of stars on the basis of this Saha's equation. In a solar spectrum, there is a important line that is called G line, or you may call it Fraunhofer dark line. Actually, this K line is due to the presence of calcium and potassium atoms in the stars. That is, the neutral calcium atom and potassium atom are responsible for these Fraunhofer dark lines. Sorry, that is, in fact, G line is due to the calcium atom and K line is due to the calcium ion, Ca plus. So you may note that in solar spectrum, G line, or you may call it Fraunhofer dark line. This is due to neutral Ca atom. And the another line is K line. This K line is due to Ca plus ion. Actually, intensities of these G lines and K lines depend on the fraction of atoms and the ions present in the star, including the sun, and the intensity ratio we can measure. So you may see that how much neutral atoms of Ca are present in a star, that determines the intensity of G line, and how much calcium ion is present in the stars, that determines the intensity of K lines. So you may say that intensity of G line, this depends on the number of Ca atoms and the intensity of K lines, this depends on the number of Ca plus ions in stars. When you say stars, it also includes sun, so you may write including the sun. Let us consider. Let Ig equal to intensity of G lines and Ik equal to intensity of K lines. We assume it. Then actually this Ik over Ig, that is ratio of the intensity of K lines and G lines, it is actually given as number of Ca plus ions per unit volume. Per unit volume. It means this is concentration of Ca plus ions and over number of Ca atoms, that is neutral atoms, per unit volume. Per unit volume. Symbolically, we write it as Ik over Ig, this equal to n Ca plus over n Ca, and this ratio is written as R. And at the same time it is found that this fraction X is equal to R over 1 plus R. I have assumed that the ratio of the intensity of K and G line is equal to R, and the fraction of atoms that get ionized is related to R by this result, X equal to R over 1 plus R. So you can see from this result that by measuring the intensity of the two lines, that is G lines and K lines, we can obtain the value of R, and if R is known, you can obtain the value of X. So we can measure R and hence X by measuring Ig and Ik. If these intensities are measured, then from the above result we can easily measure R. Simply Ik over Ig will be equal to R, and after that we can measure X. So X is also determined in this way. Now if X is determined, a relation between pressure and temperature is obtained by the Saha's equation, as you have seen this equation just now, as all other parameters of Ca atom are known. So in this condition, you can say that if X is determined, then a relation between P and T is obtained using Saha's equation, which I have just mentioned above. Since all other parameters for Ca atom are known. So using Saha's equation, we can obtain the relation between P and T. So you can see how the stellar spectra is explained on the basis of Saha's theory. Actually, the presence of the K line is due to the presence of ions, and so ionization is responsible for it. Recently, Saha's equation has been applied for developing different types of missiles. Since exhaust gas by a missile is partially ionized and follows Saha's equation, so we can estimate from that equation the pressure inside a missile, which is actually possible in the case of exhaust. So in a note, I am just mentioning this important fact that recently Saha's equation has been applied for developing missiles. As exhaust gas by a missile is partially ionized and it follows Saha's equation. So we can estimate from this equation the pressure inside a missile. Or you may say, what pressure is possible inside a missile? We can easily calculate from Saha's equation. So this is the another important application of Saha theory in explaining the stellar spectra. Now we will meet in the next lecture with some new idea, new concept.